Hello, everybody. Welcome to the MSBA program. Welcome to the statistics. First of all, make sure you're in the right classroom. Right? There was 1 year I have a student sitting here for 4 weeks and realized, shit, this is not the right place. Okay, first thing to note is this class is recorded, so be careful what you say. Right? There's a camera over there, right? All right, so this is the first class. So the plan is we would go through some of the logistic things and the overview of the field, and mostly what we are going to cover and what we are not going to cover. That's just to give you the right expectation. That's a plan. And the last hour we'll talk about the most important thing in this whole course, something about underfitting, overfitting. That's the most important thing. So that's the plan. So before I start, how many of you are full-time students here? Raise your hand, please. Full-time students? Okay. So the rest of you, everybody's part-time MSBA students, right? Anybody from other programs? No problem. Okay, welcome. So let's do the first part, the logistics things, right? First, let me introduce myself. My name is here. You can call me Tong. It's the Western way, right? The Chinese way is Wang Tong. Yeah. Okay. So a little bit things. These are not important at all, but just logistics. Yeah. So I'm currently associate professor here at the 8th floor, Department of Analytics and Operations. We were formerly known as Decision Sciences, if you have been here before. We just changed the name 2 months ago, just to ride the big wave of analytics. They just decided to change the names. Yeah. Anyway, this is my 10th year here, and I have been teaching the same for 3 or 4 years, I don't remember. Yeah. These are the ways to reach me. My office is in the 8th floor. Yeah, the side facing the sea, and you have my telephone number. I don't see the water actually. It's a port view, not an ocean view. My phone number, my email address, and my personal page. Right. So the easiest way to reach me is by email. But later we'll talk about the IDLE. That's easier. So relax, right? This is master program. Just do whatever you like. Just be careful, there's a camera. My education background, I started out as an industrial engineer in Shanghai, China. Then I did a system engineer master, basically the same thing. Then I moved to France to do the PhD in decision sciences, but essentially I'm doing the same thing, just moved from the engineering school to the business school for a better job prospect. The core is the same thing. Anyway, what else? Yeah, you can see I spent 100% of my life in schools. Sort of, yeah, pathetic. In terms of research, so I spend most of my, as a faculty, most of my energy is spent on research. Teaching is a small part of that. Everyday research is mainly on operations. So myself and my colleagues were in the decision sciences in the past. We basically do mathematical modeling and statistics and combine these to solve business problems. In terms of business, too many business problems, we basically solve the low-level, operational level things, not the strategic things. Those are hard to quantify. So we do the low-level things. And my specialization is retailing operations. Later I will show you some data about how do we incorporate data into retailing operations. Yeah. On top of that, there's some other things, supply chain and the pricing applications. So those are in terms of the context and the applications, the fields. In terms of the methodology, my core thing is actually Bayesian statistics. And here we are teaching statistical learning and machine learning, and they're two very different paradigms to build the same thing. But I think towards the end we'll touch a little bit on this. And these days I'm doing a lot about football analytics. It's a big thing. Football in terms of the football you play with foot, not the American football. So we have a lot of data on football matches, and there were a lot of this is a lot of fun than operations. You can imagine, and there were a lot of kind of cool questions you can actually answer, because in the past nobody has a lot of data about football. You have the video recording at the best, but not a lot of data. But nowadays there are all kinds of crazy data. So the most crazy kind of data set we have is like they have this high definition camera mounted on top of the stadiums, and they use the video recognition to keep track of the XY coordinates of the players, 22 players plus the referees actually, and at a kind of very high frequency, 10 times per second. So you get all these very detailed movement data. Right? So that's something we are working on. Recently, there was a big change to the big proposal of changes to the rules of football. And that was partly driven by some of the research along this line, not by myself, but by my advisors and other people. Did you hear about that? There was about 2 months ago. So there was an organization. So FIFA is the main organization organizing the football matches, the competitions. But on top of FIFA, there's a FAB or something like that, football, some board. So they are the guys defining the rules of football. What is a foul? What should be given a yellow card? And they actually proposed 10 changes to this 100-year-old game. Okay? So in this 10 changes, one was recently applied. That is about the penalty shootout. Anybody know this thing? Penalty shootout. So in a kind of a qualifying kind of this competition, when you have a cup game, if the two teams get the draw even in the extra time, they play penalty shootout 5-5, right? In the past, it's like they flip a coin, decide which team to kick first, then team A, team B, team A, team B. They have 5 rounds. And people collect a lot of data about this thing and prove like the team that start the kick first has a great advantage, about a 60% of a chance of winning than the second team. That's 60 versus 40. Although at the beginning, when they defining these rules, they were thinking about 50-50 because we are flipping the coin 50-50. But really the result is too much driven by whether you get a head or tail in this coin flipping. And there was a proposed change. Instead of doing A, B, A, B, they're doing A, B, B, A, A, B, B, A. Right? This was recently implemented, I think, in the Charity Shield in English Premier League, right? Several weeks ago. So that was one of the proposals. The other proposal that is a bit off topic, but I think that's about. The other proposal was about changing the football game's timing mechanism. So in football, whatever happens in the field, the clock continues to move. Right? It's not like a basketball; they stop the clock for anything. And turns out that creates a lot of uncertainty, a lot of unfairness among the teams, and they proposed to change that to a basketball kind of a scheme. They were saying instead of having 45, let's do 30 minutes and 30 minutes, but we stop the clock. Right? That was a big controversy among all the football fans. I think not many people can accept that, but that part of the proposal was driven by one paper along this line. So basically the paper, we have a lot of football data, right? And the paper basically showed that if on average in a football game of 90 minutes, there were 60 minutes the ball is actually moving. The other 30 minutes was wasted. Injury, substitution, all these things. On average, 30 minutes was wasted. Then, but there are a lot of situations team can manipulate this effective amount of time, in the sense that if a really weak team accidentally lead in the early of the game, they started to play all the tricks, right? So we, as fans, we all know they play tricks. But how significant are these tricks? And data shows, to some extent, these guys can make the effective playing time from 60 to 30 minutes. So in a 90 minutes game, only 30 minutes, the ball is actually moving. And these guys, the FAB or some football board, they saw this data, they were shocked. They said everybody understands there's some tricks people are playing, but they're not sure about how significant it is, and it can be really manipulated to some extent. And that's why they determined to change that to a basketball system. That's a kind of a bit controversial. So that's later I have some data to show you. We do some football analytics on the site. My teaching, I basically teach, I'm the guy teaching analytics, undergrad, master, and PhD. Yeah, all the versions. So if you want to scale up or scale down, we have other options, including you guys. Thursday I teach a PhD version of this theoretical machine learning. This is applied machine learning, and there's barely any overlap. Yeah. Anyway, yeah, there's some other things I used to teach. Are we okay? Just stop me any. Okay, good.
Based on how much you talk about football,
Mm-hmm.
can I ask
Sure.
how much of your time in research was spent on?
95? 95.
Anyway. Is this all funded by some board or something? Because
Not
it's
funded.
not using to do gambling.
It's recorded. This is illegal here, so let's not talk about that. The gambling online is illegal in Singapore, right?
Right, so are people funding your research?
No. They give me some data if you define that as funding. I got data from others. Yeah. These data are kind of expensive, actually. So there are two major sources of data. One is about the gambling market, like stock market, how the price goes up and down. I have that. And these guys have the data about football matches, what's happening, just the data I mentioned. These are commercial data. They collect this so that they can sell to the clubs. And that's very expensive stuff, yeah. But, yeah, I'm doing research. There was another question. Huh? Yeah. You said you have two.
Yeah, so how much time you spend in who funds your research?
Okay. Not the government. You're not from Singapore Pools. Singapore Pool is the only legal place you can gamble, but because they have such a dominating position, they offer very bad odds. Very bad odds. All right, so that's about myself. Administration. So what I'm about to say. So this course is called statistics, but in fact it's really about statistical learning. They are fundamentally connected, but there's some difference. On the one hand, I just put classical statistics in the boot camp. So that was the original design. I think this year, did you have the boot camp, the complete? All of you had the boot camp? No? Yeah. Yeah. But anyway, classical statistics is outdated. In many places they are wrong if we view them from the modern angle. So knowing that or not knowing that is not super important. Throughout the way, I would try to map back to the classical view, and whenever there's some discrepancies, I would try to go back and tell you, like, in the past people believed this way, and there's still people doing that way. There's a big inertia in the academic. Computer scientists changed very early, then statisticians changed recently. And those social scientists, they follow the statisticians. They're still in the back in the dark days, most of them. We are social scientists. But in that sense, classical statistics is not that critical unless you need to communicate with some people trained in the old system. You might have some challenge if you are purely trained under the modern paradigm and you have to work with a boss that is trained in the old system. You are going to have a lot of trouble. Yeah, but there's a way to communicate. But R programming is fundamentally important. I hope you have done something already, right? In the boot camp? Okay. Still have chance. Still have a lot of time. Mm-hmm. So we will do a lot of conceptual things, but at the same time, we'll do a lot of numerical things. We need to simulate the data sets to illustrate. We want to create a weird data set such that we can illustrate the shortcomings, pros and cons of some of the tools. So we'll do a lot of coding. All the assignments will be coding-based. Coding is not the ultimate goal, but that's the necessary part so you can move ahead, right? But the ultimate goal is to have some understanding of the report, but it's based on the coding result. So that's necessary. And if you're having trouble, it's better to pick it up as early as possible. Don't leave that to the end. The homework, the tests, exams, they're all in a programming way. So you'll be given a data set, given some questions, and you need to type your own codes and to answer the questions, right? The test was, especially last year, there were a lot of complaints about I actually understand everything, but I didn't have enough time to complete the code. My computer was slow, my computer crashed in the middle of the test, and try to solve that problem as early as possible. It shouldn't be the problem you realize in week 13, right? Try to solve that problem. It shouldn't be that difficult. Yeah, but we will do a lot of exercises. And the other type of complaint is, why do you give us this kind of a dirty data? Can you clean it for us so that we just do the important part? No. That's not the point. In reality, you are the one who does the modeling needs to do the cleaning, because you are the only one understand what you are going to do. Others cannot clean the data for you because there's some gap out there. And that's actually, in practice, the most difficult part and time-consuming part. Organize your data in a shape that you can analyze. That's also a good thinking process. I think that's important. I started to do that, I think, 2 years ago, because I realized the homeworks were, the data in all the homeworks were super clean. Later we'll show you, we're doing some prediction. The first column is always Y, all the other columns are always X. So people get used to that kind of a nice environment. You're given a data set, you just need to run. The first column is Y. And in the test, a lot of people don't really think about what should be my Y, what should be my X, and are these the right shape of the data? People just start to run. I think it's really bad habits, right? So let's make it a little bit more real. Textbook. You can survive without the textbook. But there's a free copy of that, so why not just download a copy? So this is the book. Most of the notations and language will follow this book. It's not easy because this is written by statisticians, and if you are coming from a computer science background, you'll find this really weird. But we're going to follow this book. The book, I put a website, this is an official website by the authors. They offer a free PDF copy on their website, so you can just download it. Legal copy, so there's no problem. We are not going to cover everything in the book. This is selected. There's some political reason later I'll tell you. But the nice thing about this book is really there's a set of YouTube videos on YouTube, so that it's done by the authors of this book. So they, at the time of publishing this book, they actually teach through the whole book. It's a bit condensed. Every chapter is about 1 hour long. So we are going to spend at least 3 hours on one chapter, one topic. So we will do a slower, more illustrated version, more examples, more everything. But I think it's a good practice to watch the video beforehand. So before each session, I will announce what we are going to cover next time. This is chapter 2 next week, and this is the corresponding videos. Have a look and have a preparation what's going to come. And feel comfortable if you don't understand everything. That's a bit quick if you don't have the background. The other one is the reference is a thicker book by the same authors. That's the PhD version. Just in case you're not really satisfied by my superficial introduction, you really want to know the underlying math, there's a place to find all these things. Right? I think that's relatively more accessible than an average PhD textbook. Okay. Any questions? No problem? Okay.
Sorry, I think something wrong in the link or something.
The second one, right? YouTube videos? Something wrong with that? It's also on our system. I'll show you in the next slide. Okay. So that's the books. So when I was doing my PhD, I had a kind of an illusion about these yellow-covered books. This is the standard set of a Springer text. There's a Springer text on mathematics, and they're all crazy books. So whenever you see this color, you get assessment. I hope you don't focus too much on a grade. I hope you're adults. They're two undergrads, but don't worry too much about the grades. In the past, I've never seen any employer really check your transcript at the time of the interview or all these things. So don't worry about that. The project you do and the interaction with them, that makes much more important influence on that thing. But NUS is very kind of serious on these things, so I have to declare this thing, right? So there'll be 10% on class participation. I don't keep any physical evidence of what you have done in class, but it's based on my impression. Just to clarify, this is subjective. I'm very biased. Don't come back and ask me for evidence. I don't have one. Assignments, we will have, I think, six assignments, but this is group-based. So feel free to discuss and collaborate with your team members. And if your group has problems, it's fine to talk to other groups. But the important thing I want to emphasize is don't really have a super clear cut on the allocation of the jobs. One guy doing the slides, one guy doing the coding. That's not healthy. You are going to do the test individually. So the coding part, even if you cannot finish that on your own, at least I think at the time of submitting this assignment, you should understand everything in there. You should be able to do that individually, right? Otherwise, you'll have big trouble in the individual exams, right? And that's the individual exams. We will have two. One in the middle, I think after the middle break, we'll have an exam, and one in the last week, about half of the session, 90 minutes. If you need, I can give you more time. But that's in class, individual, so you do on your own computer, right? So make sure your computer works. There are people like in the exam, they're installing RStudio. So Yeah.
Is it open book?
Yeah, open everything, open internet. Yeah, we'll talk about discipline later. But just think about in practice. The only constraint is time. You only have this amount of time. Yes. Yeah, that's it. Yeah. Yeah, the other constraint is individual. Yeah. And at the end, there's a final project. So the difference is, yeah.
Can R run on the Mac?
Yeah, of course. It runs better on a Mac. In the past, those who have their R crashed are all Windows. Especially when the data is big. So yeah, Windows is having some troubles. Where was yeah?
Is it possible for us to have the in-class test in the lab or somewhere?
You can do it anywhere. I'll have this classroom, but if you really need a kind of a quiet room, you can go to the library.
No, I mean
You want to use others' computer? No, that's too much risk. You don't want to use a school's computer. I don't use this thing. It's too much risk.
I mean the classroom can be changed to the computer science.
Why do you want to do that?
Because we actually got Mac, Windows, sorry.
But you have to install every packages on the spot.
Yeah. No, just now you're saying that most of the crashes happen on Windows. So I'm just worried.
I'll give you past year exams, and you have an opportunity to test your computer. It's time to buy a new one. Yeah, but you need to work it out. You're an adult. Final project is somewhat like the test, but it's just not defined. You do whatever you think is interesting. Find your own data sets, find your own problems. There are a lot of online competitions. So in the past, people either they have their own data sets from somewhere, or they participate those Kaggle competitions. We have several competitions. They have well-defined problem and data set. So, but most of the time, the competitions, the data is too massive. You can take a subsample just for the sake of your project. That's fine. Yeah, but try to find your own problem. If you really have no idea what to do, I will try to help. But I don't guarantee the quality of the things. Right. All right. Are you okay?
So how many people in your group?
I think 5. I have it somewhere. Not here? Oh, yeah. No, 5 to 6 assignments. That's not a group size. Let me show you here. I guess did anybody showed you how to use IVLE? You all know this thing? I don't need to explain, right? But there are several important things I want to highlight. Pretty much all the interactions will be done online through this thing, all the formal things. Several things to note. Lesson plan, I published the schedule on the lesson plan. So before every session, roughly around the Thursday evening, or at least at the latest, I'll post what's going to show up. No, I'll post the plan there, but I'll put my slides around Thursday evening. Right? So the slides will be online, like today's slides is here. But I will do some writing on my slides. So after the class, I will update that with those ones with my writings. But before the class, you should, tonight, you should see the plan for week 2. I'll update what's going to be covered in week 2, what the corresponding chapters in the textbook, what are the YouTube videos you should have a look, and the slides will be slower. And there are other things like demo code. I'll post my code there I used in the classroom, and assignments and assignment solutions, all those things. Right? So keep track of lesson plan. That's the most important part. What else? Yeah. Another thing is there's an amazing function called anonymous feedback. If you have anything you don't want to discuss in face-to-face, there's an anonymous function. The good thing is I can reply to that without knowing who you are, so we can discuss. Right? That's not easy. Yeah, just let me know if it's too fast, too slow, too superficial, too trivial to you. Then files. I guess somebody should have shown you this thing. I just want to highlight the assignment should be submitted here. Later you should be able to upload your homework here. Right? That's the files. And the textbook, I put it here, readings. There's a textbook, there's some web links. If the links earlier was not working, you should try these ones. I think it's still working. Yeah, it's working. Still there. So that's IVLE. Yes. Yes. Next week, before next class. Yeah, roughly next Thursday. Yeah. Next evening of next Thursday. Give me a morning to read through. Not enough?
One assignment every week or?
There's a total of 6, so on average 2 weeks each. Yeah. One assignment in every 2 weeks. But yeah, it's not evenly spaced. Come on, you have 5 persons in a group. Yeah, how many? We have 48 in, I think I have 48 in this class. Right? I don't take participation. I have 48. So you are from G1, evening class is G1. So from this evening you can, I have already predefined 10 groups out there. And from this evening you can self-enroll yourself. So far there's 0 in these groups, but the maximum is 5. So just put your name somewhere. Talk to your peers and put your names in a synchronized way. I think maximum is 5. We have 48 students, so we have 10 groups, right? 5 is about ideal. Huh? It's okay? What did I? Yeah, also when you form group, I think try to have a diversified combination. Coming to a program, the important part of that is to learn from your classmates, right? Yeah, otherwise you can sit home, watch videos doing Coursera. Right? So, the important part is to interact with your classmates. Try to form a team with people with different backgrounds and learn from each other. Right? Some people having more working experience, knowing more about the business. Some are better at programming. Some are better at getting data, all these things. Right? And the point is not to allocate the jobs. Right? The point is to learn from each other. Right? That's the grouping thing opens tonight, 11 p.m. Yeah, this is automatic. Yeah, we finish it. Yeah, I don't remember why 11, but you have 1 week to do that, right? So within 1 week, if you don't put yourself anywhere, I just randomly put you in an empty slot. All right. That's logistics 6. Huh? Next about the.
Do we know the dates of the test and the final group project now?
Test is the last week, the week 7 and the week 13.
Before the recess week?
After the recess week and the last week. Group project, you have another 2 or 3 weeks after week 13. So the official NUS calendar is after week 13, you have a reading week, you have 2 weeks for exams. Then the following week, I have to submit your grade. So I cannot go beyond that point. So I'll give you maximum amount of time. I give you myself 2 days for grading. All right. We will talk more about the project. I think there was some trouble because the real useful things will only be taught close to week 8 or week 9. So, but I think you should try to look for the topics early and start to the pre-processing part, and you will learn some other things. Use some simple tool to work the flow first. Then you can replace the simple tool later when you have a better tool. And the project, I will need a report which functions like an appendix, technical appendix. The main thing is a video presentation. We don't have time to do presentation in the class. That will take 2 weeks. And every group submit a video presentation. You just use your phone, shoot a 10, 15 minutes presentation. Just like when you talk to your client. We have done this project. These are the main things. The high level things. Find what are the problems, what you have done, what are the findings, the result. And the technical appendix is the written part. Right? So I'll mostly just look at the videos. Unless I have other questions. All right, so next part is about the high level blah blah stuff. I promise that's the only 1 hour of these things. I put it here because I think it's important to talk to outsiders about what you're doing and why it's significant. Right? So I just put some summary of that. That has nothing to do with really what we are doing here. Right? So the first thing is big data. I only have 3 slides on big data. After that, we will no longer mention big data. And after taking this module, don't claim you learned how to do big data. We have nothing big data. Right? Everything is small data. We always try to correct others. Now, we talk to practitioners. They will say, "You do data. Oh, you must be a big data guy." No. We're a small data guy. We don't do any big data. So this is the Harvard style kind of stuff. This is big data was originally written in 96 or 97. This is a Davenport Harvard Business Review article on the age of big data. Basically trying to kind of characterize what's the critical difference when we are moving from small data to big data, right? What's the critical things we need to worry about? So they summarize this in 3 V's. I think later somebody else add another V, but I only have 3 here. The first V is volume. Volume should be intuitive, right? When we talk about big data, the first thing is we have more data points, right? So what do we really mean by a data point? Anybody has how do we define a data point? When we say we have a data set is a collection of data points, right? What is one data point?
One whole set of data that describes all the relevant features of the object.
Yeah, one object, right? One entity, right? So if we're studying customer, there's a collection of customers, and we have some data describing one particular customer. Information about all these guys is one data point. Yeah, so that's something. Later we'll come back to this point again, but in some sense, whatever we are going to analyze, at the end of the day, that becomes a table. Becomes some table with n data points. Every data point sits in one row. Every row is one object, one entity in this data set. We have n of them. Then every data point has some features. If you're not comfortable with this word, call it attributes. Something describes this data point, right? The age of the customer, gender of the customer, income of the customer. There are many things. And there might be something like Y. We'll come back to Y later. But yeah, for each data point, we have a vector of numbers describing their information. Right? When we talk about the big data, the volume in the big data, the message is really this table is going to be longer and longer, right? We are going to have more data points, right? This table is going longer. Right? So what are the pros and cons? Is that a good thing or bad thing? In what sense? Right? Bad things should be clear, right? What are the bad things if you have to? Yeah, you need more powerful computers. You cannot use Windows, otherwise it will crash. Right? So you need more facilities, more memories, and if it's even bigger, you need a distributed things. One computer cannot handle that. You need to think about a parallel solution, all these things, right? How about the good things? Yeah, so when we do analysis, more data is always a good thing because that would improve the accuracy. Later we'll try to define this accuracy. And actually this number is a supercritical number. Yeah, we'll come back to that later. So that's I'm not going through the figures. I guess you can easily be convinced. And the other V is a variety. Variety basically says, yeah, in the past, when we describe a customer, maybe they just several things: age, gender, marital status, all these things, right? But nowadays we have all these record about the customer, what he posted on his Facebook. His short piece of a video when he was doing a vacation in Maldives, right? The images he posted, and the check-in data, and text he's talking about, and all these things makes the attributes about one entity much more rich, right? There are more things. So in our earlier language, this is basically saying before you have x1 to xp, and now this is going to be wider. Right? You are going to have many ways to describe one data point. Right? And again, the challenges are similar, right? Well, when you have more things on your table, then there's some physical challenges, also there's some analytical challenges. But the main challenge they were trying to highlight here is actually all these things are not a traditional thing we put in a table, right? We said every analysis we start with a organized data table, but how do you put a video in a table? You have to put one number to describe something, right? How do you put that? And that's another level of challenge. That's more related to this structured data versus, sorry about my handwriting. Right? In the past, we all have structured data. Do you know the difference? What is the difference between structured and unstructured? Anybody? You know?
The moving data will be the unstructured.
So how to define unstructured?
For example, the traditional SQL table can be the structured.
Yeah. So whatever can be easily put in a table is a structured data. There's a column, and we know this column is for income, and there's a number. We know that number represents the income of that point, right? But there are a lot of things is very difficult to put as a column, as a spreadsheet kind of a shape, right? So this is basically unstructured, and so we need extra tools to convert all these unstructured to structured data, and there's another level of challenge, right? How do you convert the video into some attributes? It may not be one attribute; it can be many, right? But how do you convert them? And it can be huge number of attributes. Let's add another level of things, right? Okay, that's about the variety. Then third thing is about the velocity. Velocity, this is not the main point about velocity. This is about the data has been increased in exponential speed. But the true velocity issue is really the time you have to respond to something. So 100 years ago, if you want to do a survey on people's income, education, you have 1 year or 2 years to do the analysis. That's perfectly fine, right? But nowadays, the time you have to do some modeling and analysis and to do some prediction is really shrinking. You really need quick and immediate response to your customers. I think 2 years ago, we invited a guy from Facebook marketing here, Facebook Singapore. He's in charge of marketing, and he's not dealing with the Facebook users. He's dealing with the advertisers. The attract advertisers to pay to Facebook. So he shared what they are doing. So they said they're doing customized video delivery. There's some fancy words, but the whole thing is about when the customer opened the Facebook app, started to scrolling down, checking all the posts. Every several regular posts, you will have a slot for video advertisements, right? So whenever you start to scroll down, Facebook needs to decide what's going to be the videos to show to you as a particular viewer. And they want to maximize their revenue by showing the right advertisement and attract many clicks, right? And they find this is too difficult. They don't want to do that, and they had a smart idea. They basically created a exchange, right? They talked to all the advertisers. They said, you guys get ready. So we have such an IT platform. Whenever there's a user started to scroll down, in about 2 seconds, the user is going to reach that video slot. So we are going to send off you the information about this viewer. What's the most recent post you have clicked? What's the most recent check-in? Have you click any video related to sports, running or cycling, all these things, right? Facebook will sell pretty much thousands of your histories in terms of labels, your attributes. Send this to all the connected advertisers. And they gave the advertisers 200 milliseconds to respond. I'll give you this information. Tell me how much you want to buy this guy. So whoever offers the highest price will have their video played to this viewer, right? And their challenges are, so their customers are like a P&G, Unilever, Adidas, all these consumer brands. And they don't have that capabilities. They were thinking about how do we help these guys develop an algorithm to respond in 200 milliseconds, and to decide what's the value of this guy to me, what's the fit, right? That's kind of the things. So 200 milliseconds, that's what they're doing. So that's velocity. But after you have done this thing, you will see 200 milliseconds is nothing. You can easily do that in several milliseconds. It's about using a trained model to predict something. It's not about training the model itself. The training the model takes a lot of time. But applying that model on one extra data point, here's a new viewer. I know this attributes. How much does this guy worth to me? It's just a prediction on one data point. That's nothing. The difficulty is really on the back end. How do you get a model to predict, to estimate the value of a viewer? All right, are we good? So that's the 3 slides about big data. We're done, right? So we are getting back to the small data world. So this is master's in business analytics. I think I should have to talk about business analytics a little bit. In some sense, the new thing is the business, right? On top of the analytics thing, we need to use analytics to solve business problems. That's roughly that thing. But I didn't find very good definition other than this one from Wikipedia. I don't know who, not WikiLeaks, but Wikipedia. I find this good enough, right? There were several important key phrases. Business analytics, right? The first thing is we need to explore and investigate past performance. This business is the action, right? So we need to look at the past. If we have a data set describes the history, and we need to understand what's going on. Right? After you understand what's going on, you need to. This is more like a what kind of a question. What happened in the past? Then you need to gain insight, like why things happened that way. Right? Why? And after knowing why things happen that way, you can think about optimized future. Right? How to make the better decisions for future. Right? There's multiple levels from the past and understanding the mechanism and project that into the future. Then if you think along that way, there's a graphical representation of the same phrases. Basically, that's talking about the same thing. There's a what and the why part. So I want to cut this into 3 pieces. So the first piece is about the what and the why part. This is more, we call that descriptive analytics. So it's describing what's going on and why things happen that way. Mostly look backward, look at the data set. And there's another part on what about the future? What's the trend? What will happen? So this is the second part. This is the predictive. And the last one, if you can predict the future, you can choose the best decisions. So this is prescriptive. So just to draw the line, descriptive is mostly the visualization thing. How do you represent the data, show the pattern, the traditional statistics in understanding what happened. We are not doing so much there. So pretty much everything from this course is on the predictive part. This is the predictive analytics. And the prescriptive part is really about optimization. Given your understanding about the mechanism, how do we choose the best thing? This is optimization. So we have an extra optimization class on this. So we won't touch too much on that. Right? So this is where we stay. Yeah, that's not important. Right? That's the continuous improvement. I guess this. Here, continuous and iterative process. Right? So after one round, you can continue another. From a slightly different perspective, this is a food chain kind of a perspective. Who stands on top of the food chain and who is on the bottom. Right? So there was this data coming through this whole process that's being transformed along the way. So we start by having a problem, then we get some data. Right? So at the data stage, there were a lot of issues. Main thing is data collection. What kind of data you want to collect? How do you collect your data in the cheapest way? Later I will show you some of the stuff I have done. And, yeah. The fancy word here is Internet of Things. Right? So you have a lot of sensors deployed everywhere. They're connected to the internet, so you get a real-time reading of many things. So you get a lot of data. And converting data from information, mentioned this is the visualization, guys. And some of the classic statistics, trying to summarize. Nobody wants to read raw data, so how do you frame the data, present the data in a more human, understandable way? So that's the part. That's not our main thing. And from information to knowledge, that's the statistical inference. That's then from knowledge to decision is the optimization. So you can see this is a food chain. We start from the very bottom and data being processed along the way. And think about my department, most of the people are doing optimization, this kind of things, right? So we are standing on top of this food chain, and that's the worst possible situation because whatever you do, it really heavily dependent on the previous stages. If people don't do a good job there, your things won't be very meaningful. There's a lot of dependency I want to emphasize, and the ideal way is you connect everything together, right? You do everything. Right? I'll show you something in 2 slides. All right, we're done with the high-level things. Some quick examples. Huh? Anybody know what's here? Anybody heard this other story? What? Process of giving birth. I'm not good at that. No one heard about this target?
Target predicted what kind of products or stuff that pregnant women will buy in the future?
You really don't know? No. That was a big fuss 2 years ago. Okay, maybe you're too young. So about 2 or 3 years ago. So Target is the supermarket chain in the U.S. You know that part? The story? Okay, so the Target is the confusing part, right? I should have a trademark here so people. Who knows that story? Can you tell the story? Come on.
I don't know. I'm in the store.
Okay.
Is it about the target knew that the girl was pregnant?
Yeah.
She even knew about it.
Yeah, can you share the stories?
I forgot like some.
Come on. So that the punchline. Let me get the punchline later. Huh?
The father received a brochure on the
Exactly.
pregnancy product,
Mhm.
and he was pissed off that why are you sending it to me?
Now to the teenager girls. Huh?
Yeah, so now for his teenager girl was pregnant.
So the story is like Target is sending these coupons or some promotional materials to this guy, and he was pissed off. Why are you sending this thing? Why do you think I would need that? But he has a teenager girl, and it turns out the teenager girl was pregnant. And the teenager girl has been using his father's member card to buy things from Target, and Target, by looking at their shopping history, figure out there's a woman in early stage of pregnancy, and that's the big battlefield in recommendation. Once you identify a pregnant woman, you know exactly at what moment they would consume what kind of products, all the way in the next 5 years, right? Think about that. That's a big battlefield in online. That's the easiest place you can recommend the things. You know what they're going to need, right? So they just send all these promotional materials to this father, and the father was pretty mad. And turned out that the girl was actually pregnant. So that made a big punchline on the media, saying Target knows the teenager girl is pregnant even before her father. So that was the punchline. Then there were some interviews about the analytics group at Target. How did you guys really find it out? So we have big data, we have all these things. But eventually he explains. So there's a clear pattern, shopping pattern. So the member has been buying some type of body lotion for a pretty long period. They're pretty loyal to something. But suddenly they switched to a different type of lotion that is claimed to be pregnancy friendly, that kind of thing. Right? That's a big signal. They capture that signal. They realize this must be pregnancy, and everything is reasonable, right? But that made a big thing in the media because people are talking about privacy, right? The family doesn't even know, but some random supermarket knows. That's not the right thing. So that's a whole story. Something. Never mind. But as a people doing the analytics, right? How do we criticize this? This is not the right way to look at this problem. There's something missing. Can anybody see something missing? Not about the privacy, the legal things. Let's leave that to the lawyers. But think about the prediction. Is there anything missing?
If you're able to predict something before it comes happen,
Yeah.
not before,
Yeah.
they should happen.
Uh-huh.
That would be a plus point. Like, over here, we could predict that lady is pregnant much before she had any born baby.
Uh-huh.
Then, let's say in the real-time industry, you can predict something is going to happen.
Mm-hmm. Yeah.
Well before ahead. So that
Yeah.
can save us the cost or the maintenance
Yeah.
or all this stuff.
I'm talking about the criticize. What's wrong here? What's right here is uh-huh. How do you define accuracy?
The data picture, I think it's a simple two-way prediction.
Mm-hmm.
So of course there will be some blind spots.
Mm-hmm.
So basically the prediction to be wrong.
So now suppose if you are you are the analytics guy working at Walmart, you really want to say these guys are not doing things right. That's not the right way to say Target has a super powered analytics engine to know everything about the customers. How do you criticize this?
The other reason why people change their shopping behavior
Uh-huh.
for the particular case, maybe use other reasons, and those can make the customer choose a different type of person.
Yeah, it's getting close.
What do you think it was the guy that they were sending it to?
Uh-huh.
Well, it was a man. So wouldn't you have thought that extra data set should be...
Good point. Good point. No, this is the father owns the membership, right? I think that the point is, you know, this is a guy, and you're sending this thing. That's a good point. Yeah. So that's not the main thing. It's not the well.
Data privacy.
Let's not touch the privacy thing. Think about. Do you think this is the way to sell your prediction? If you have a prediction algorithm, how do you want to convince people like my algorithm has a super accuracy? Yeah, you need to show some aggregated statistics. You cannot show this is my best ever case. There's only one case, right? It's well possible Target sent 1 million coupons about diapers to everybody. That might be possible, and they happen to have this story. It could be, right? So what you want to say, I have a super prediction. You want to say, I predict 1 million customers and manage to grab 1,000 out of them. Right? Nobody can do that, can reach that accuracy. Right? So there should be an aggregated thing. Right? This is the later we'll talk about. This is the true positive. You predict this guy is positive. That happened to be true, but there are a lot of false positives. You predict them to be positive, it happens to be not true. And the important thing is not just to look at one side. The other side is very important, right? If you're making a lot of false positives, yeah, you can still happen to have something like that. Mm-hmm. So that.
But nobody would, like, this is just one specific instance when the dad got, you know,
Mm-hmm.
and then that's why it became big, right?
Yeah.
When the dad found out. But
Mm-hmm.
maybe, like, we don't know that maybe it has been successful. So how would you...
Yeah.
I don't understand why we're criticizing that.
No, we
One.
cannot make any judgment based on one particular case. That's my point. And later we'll talk about how do we evaluate one prediction algorithm. It should be based on aggregate. It's based on how many false positive and how many true positive you have. Right? That's a true measure of success of some algorithm.
So you think Target should have done more?
No, I think that the media over
Yes.
interpreted this thing, right? Over is not some magic. They just know every customer there, whether they're fragments or not, right? It's an overreact, overinterpret. Okay? Good. This is Uber. This is 3 years ago. We have a PhD student. He went to Uber to apply for a job, a data scientist, and he got a interview question, a set of 4 questions. He was given a whole day to do a take home. And there were 4 questions. You choose one, and you do one, and you submit within 24 hours. But he actually came to us. We got those 4 questions. I didn't help anyway. So I just secretly steal the data. I didn't do anything. So so actually, this is one of the questions I find it more interesting. This is more like a pricing problem. So they said Uber give them 1 week of data about the number of logins. Every time you open the app, that's counted as 1. This is in San Francisco area, a sub area. It's not even a whole city. A sub area in San Francisco. 1 whole week of data. I think in the granularity of like seconds, minutes, I think. Right? I don't remember exactly. So we just plot it out. And the question is, how, given this is basically the demand pattern, right? When people open the app, they're looking for taxi, right? They're not checking for coupons. But this is basically the demand pattern, right? How do we design a peak time pricing schedule based on the information here? So that's the question. Can you do this? Have any thoughts? Well, first of all, let's try to read the data. The data is pretty intuitive. First 5 days are weekdays, Monday to Friday. Then you have Saturday, Sunday. There's a weekdays. There's a lunchtime peak, and there's an evening peak. It's pretty standard lunch peak. Is that lunch or morning? Yeah, I think the starting point is a bit weird. You cannot have a high at the 0, right? that's midnight. I don't know I don't know the definition of time. But there was what? Yeah, I guess this 6 to 6 probably. Yeah, but there's a clear pattern. There should be a lunchtime peak and an evening peak, right? And the weekdays are pretty much similar, but Friday can be crazy. If you look at the variability, the first 4 days are similar, but Friday sometimes can hike up a lot. And this is Friday evening. It's clearly different. And weekends, there's some morning things. People go out, and so you can tell some stories out there, right? But we just struggle to you can easily identify the peak hours and non-peak hours in a week time frame. But how do you do a pricing here? What is missing here? Yeah, exactly. There's no information about the supply, right? If the supply follows exactly the same pattern, then that's an easy problem. Right? So you need to know the supply. Actually, it doesn't have that. So we didn't do much out there, but basically Uber was showing this data and asking for a proposal. You don't have to do anything, just asking for a proposal. Given this data, or tell me what kind of other data you need, how are you going to proceed to come up with a pricing thing, right? So that's the kind of let me not spend too much time on this. This is the next two of my stuff. I promised to tell you some about the sensor stuff. This is what the retailing operations. I have been working with retailers, not online retailers, real retailers. This was 2014. The data was collected 2014. So 2014. In those days, kind of traditional retailers, they're really pessimistic about their future. They were thinking about the online retailers are eating up all the market. They have a hard time surviving. And if you ask them what's the disadvantages, what are the things you cannot compare with them, they will mention the rental cost or all these things. Right? That's the standard. Then, interestingly, they will say, we have a big disadvantage in terms of data. Think about what an online retailer would know about their customers. From the moment you open their website, they know you are here, who you are. And they know you click a particular button, you stay on this product page for 25 seconds, and you are scrolling down, you're actually reading, and you put that in the shopping cart, and you delete it later. All these things, they know every single movement you have there. And they said, what do we know about our customer? We know nothing. We're lucky if they buy something, so we have a transaction record on the cashier. But otherwise, we know nothing. So those days, the discussion was, can we do something to match the data capability of an online retailer in an offline environment? That was, nobody knows how to do that. But those days I was doing all this robot kind of stuff. I said, I have a lot of sensors, toy sensors. Maybe we deploy some of the toy sensors into the shops and just see how it goes. I would just put a lot of sensors. They're cheap anyway. You just put a lot of sensors, and the ultimate goal is let's try to get whatever the online retailer can have, we wanted to have the same kind of data. It turns out, the one thing we cannot do is about the customer identity. The online retailer always know who comes here. Right? There's some cookies and you keep your login. But offline, that's difficult. It's very hard to know who you are. We were trying to do some face recognition, putting a camera in front of the entrance, shooting outside whenever there's something. But that's a privacy issue and all these issues. So we didn't do that part. But all the other things we managed to have some counterparts. Like this customer walking into this sector, we have all these ultrasonic sensors to identify, there's a guy standing here. And you can also use video cameras. And the important thing is they are not satisfied with, like, I don't just want to know there's a guy standing here. I want to know what he's doing, which product he's looking at. Is he choosing between the two or all these things? So eventually we put some sensors on the shelf. Actually, we just put all the products on the same plate, and the plate is sitting on a scale, electronic scale. It's basically a weight sensor, a very cheap weight sensor. It was so cheap, like 10 Singapore dollar for that sensor. We didn't expect very good readings, but it turns out to be super accurate. So accurate that this is the data you see. This is the test we have done with fresh vegetable retailers. They're selling all kinds of vegetables. So by doing the experiment, I think I remember this was the white radish kind of a big thing. So we just put the product on top of a scale, and we read the weight data 3 times a second. So that's a small clip, I think 90 seconds about what's happening. So most of the time, nobody is touching that, so it stays the same. It doesn't move. So this is the moment somebody comes in, actually pick up one thing, holding that in his hand, and the other hand is still digging, trying to pick for a better radish. And he was stopping there, thinking for a while, several seconds, and maybe, shall I get another one? Just another round of digging, but didn't do anything. But then this guy disappeared. So at the end, you can see the change in the weight is about 1.8 if you measure. This is in terms of grams, so 1.8 kilo. And several minutes later, we have, this is 10:38, right? 4 minutes later, we have that transaction show up in the cashier's database. Actually, this guy bought 1.79 kilo of radish. So you can match all these things. We didn't know they were so accurate, so there's not much noise out there. So we can easily identify there's a customer shopping for this thing. He spends how many seconds picking and how much he has bought and when he made the payment, all these things. So we had a lot of fun there. Just something to show. And eventually we use that to build a model on product choices. So there are different products in the same category. There's a white radish, red radish, or something. Don't remember. But how customers choose between these depending on the price. The price fluctuates a lot. We did the choice, and eventually the final decision is how much of each kind of a product you want to carry every day. This is perishable. And how do you price that? Whenever one product is sold out, how do you change the price of the other products because they are kind of interdependent? We did some experiments out there. So this is more illustration of we are controlling the whole food chain from the data collection. So we have a real-time reading. So those days my job was sitting in my office in Singapore reading this thing. So the shop is somewhere in China, so reading this real-time data and trying to guess what's going on. And eventually this data is built into the model, and we make some decisions out of this. That's my favorite part. Can you guess what's this? What's the data about? This is one game from minute 0 to minute 90 full time. This is one game. The timeline is one football match. 2012, Southampton, Manchester United. There's no gamblers here? Huh? What are these?
Position of the player?
No.
Position of the player?
No, there are only like 3 numbers, right? No, this axis is time, right? This axis is from 0 to 100%. No. Probability, right? Good, probability. We have 3 probabilities, right? What are these? Win, lose, draw, right? So basically red stands for Manchester United. Blue is Southampton. Green is draw. At minute 0, this is the data we got from a gambling website, right? This is the market price for the offer odds for the 3 outcomes, right? So we convert the odds into probability, so that's easier to read. So that's basically the market belief. At the beginning of the game, market believes Manchester United having 60-something% of a chance of winning, and there's 20% of a draw and 15% of a for Southampton, right? But the fun part is really the evolution. This is in-play gambling, so the bookies offer the odds in real time. When the game is going on, the bookie is changing the odds dynamically, and we capture all this data and do want to show in one game how the probability is being changed. Can you see what's going on? In the first several minutes, nothing is happening. When nothing is happening, to find this intuitive, the green area is spanning out. Is that intuitive? What does that mean? This is the probability for draw, right? If there's no goal, this green area should expand to 100% towards the end, right? That's going to be a draw, right? So it's spanning out if nothing is happening. The funny things happened minute 15, Southampton scored a goal, right? Southampton scored a goal. So the winning prospect for Southampton is jumped jumped to kind of almost 30%, right? And Manchester United dropped. Jaws stay pretty much the same. Right? So market is pretty kind of efficient in that sense. Later, 7 minutes later, Manchester United scored. Then they all jump back, almost back to the original trajectory. There's a trajectory going all the way to the 100% jaw. Something like that. Right? If nothing happening, the green thing should go out like that. Right? So we actually have a paper proving this thing. Anyway. So you see nothing is going on. Then Southampton scored another one because there's not much time left. So Southampton's prospect is much better. And as the time is kind of going out, Southampton is having really good chance out there. But in the last 5 minutes, Manchester United scored 2 goals, end up having 100%. Right? So that's the dynamics of this thing. Right? Think about how they managed to get this. So if you're running a bookie, you need to offer these odds in real time. How do you adjust whenever there's a goal? How do you adjust that to have the more kind of a fair odds for the results? Right? This is a difficult question. So that's something I'm working on. Actually, I have a better one than this, I think. Yeah. A lot of jumps are driven by extreme events, right? Having a goal is an extreme event that definitely affected the outcome. So you might have a red card, suddenly there's some jump. You might have some injuries. This guy seems like injured, but after a while he stands up and he goes back and all these things. Okay? Yeah. So there was a lot of things can be done there. Okay? Let me see how many more slides. Let's have the break. Let's have a break. Is 10 minutes enough for you? Okay. Come back. Okay. We spent 30 minutes? 20, at least 20. All right. These are, we talk about some examples, right? Next, we have something about categorization of different type of learning tools. This is not so critical, but good to know. It's good to know where we are. So we talk about statistical learning. I'm using the word statistical because the book is using that. It's just replace that with machine learning. It's pretty much the same thing, right? So and the learning, there are two major cuts. The first cut comes whether your learning is static or dynamic. Static means there's a data set. The data set is there. It never changes. You do your analysis on the data. Right? That's static. On the other side is the dynamic. So the data comes back in a stream. So that's sort of the so-called reinforcement learning. And the easy situation is your data comes back one by one. That's not even reinforcement learning. That's online learning. That's a simple situation. The more difficult situation, think about the AlphaGo. That's a good example of reinforcement learning. It's really when you do something, you don't immediately know what's the consequence. And you have a decision, but you don't get your feedback immediately. So there's no kind of feedback, no response. You will never know. For a human, it's very difficult to estimate how much value should be attributed to this particular move, because I'm doing many, many other moves in the future. Right? So that's super difficult things. We're not going to talk about that. So most of the stuff we are going to talk about are static. There's a data set cleaned. We don't talk about data cleaning in class. There's a data set cleaned in a nice spreadsheet shape, and we're doing the analysis. So in our sites, we can further split that into supervised and unsupervised learning. Most of the effort will be spent on supervised learning because that's the easiest and the well-established. Everything is well-defined. That's a nice word. And supervised learning, my personal opinion is this is more important, but it's really not much there. Well, I'll give you more details later. This is about the reinforcement learning. That's not important. I put a link there showing how AI plays some of the simple video games. And by trying kind of a million times, AI actually figure out many, many tricks human never realized they exist. Right? You can check the videos. This is a paper published in Nature, and they have two attachments that are basically videos. So supervised learning. So we talk about, we spent most of the time on supervised learning. So what's the definition of supervised learning? We said supervised learning, the biggest thing is well-defined. You have a clear target at the very beginning. We want to predict the income of a graduate 5 years later. Right? There's a clear number we have in mind. We want to know that. So we call that Y. But that's our target. And depending on where you come from, there are multiple ways of calling Y. Some people call that outcome. Some people, in stats, we call that dependent variable. In computer science, they call that response, target. Yeah? They're the same thing, different dialects. And in order to predict the income of a particular graduate, we need to collect the information. Right? So the other piece of data we talk about, this is a vector of X. So a collection of attributes for each data point. So we call them, this is one-to-one correspondence, right? Input versus outcome, independent variables versus dependent variables, features versus response. Features is the computer science word. Covariance is the stats. Features, covariance. We use those things interchangeably. We don't try to differentiate. And also we use predictors somewhere in the book. Regressors is very specific to regression. We don't need to talk about that. Predictors. So the variables we use to predict Y are predictors. And having this bunch of X and Y, then we have a data set. We have n such data points. That is our data. And then we call this data set. Sometimes we call that sample in statistics. All these things. So what's the goal of supervised learning? Because we want to predict or say something about the relationship between X and Y. So we need to, the ultimate thing is to find out what exactly is the relationship. And this is a bit not so rigorous, but you can somehow think about, because X and Y has some relationship, we can think about Y can be represented by two terms. This one term is driven by X. This is a function of X. Right? tell me X, I'll give you a number there, and plus some noise. Right? So this is noise exists everywhere. This is to handle the situation where two data points might have exactly the same X, but they may, like two graduates, they have exactly the same grade, the same background, all these things, but they may not have the same income, right? Just to make sure there's some other things we cannot capture. So in the statistics, we say these are the features we can capture in our data, and we believe there are other features affecting these incomes, but we don't have data about those things, so the only thing we can do is treat them as just some random fluctuations because we don't have data. Okay? So that's to capture all those n recorded factors. So the whole thing is to uncover the relationship, and basically boils down to those two things. What is the shape of F, and how big is the error? Right? That's a supervised learning. Well defined, and if you end up having an answer, you can measure how good is your answer. And later we'll talk about that. And having this F, there are several types of kind of usage. Some people use this F to make stories. This is the so-called inference. We want to say what are the factors is going to affect the potential income of a graduate. Right? Like a grade may not have any effect. Just an example. So that's the story part, saying something about the underlying relationship. In a graphical kind of representation, just think about I have a Y, I have a bunch of X. I want to say how X actually influence my Y in my data set. Based on the data set, this is what I can say. Then on the other side, we can do prediction. Right? Most of the time, we don't spend too much time on inference, but whenever possible, we will try to add some interpretation into the results. But the main thing is prediction. The prediction, so technically there's no difference. We still need to understand the relationship. But really, the emphasis is not about the story here. The emphasis is really when I have a new data set, since I know there's an F connecting X and Y, when I have a new data set, X prime, I don't know I have a new bunch of students, I don't know their income, because I know there's an F, so I can apply my F here and say something about Y prime. Right? What would be these guys' income, given their grade, their anything. Right? So that's a predictive. We basically borrow this relationship and apply that to future data. Right? Predictive. And the questions remains like how do we measure the quality? So there are two types of tasks. How do we measure the quality? Inference, let's not talk too much about that. This is econometrics kind of a question. But prediction, we'll talk about how do we measure. What is a good prediction? What is a bad prediction? Right? So, quick example. This is mainly to show you the impact of the noise part, not the F part. So, suppose we have a data set. Simplest possible data set. There's one Y, there's one X. X is supposed to be a vector, right? This is the smallest possible X. And we have a bunch of points here. The true F, this is a simulated data. Let me stop here for a while. So this is a simulated data. This is not the real life data. In real life data, you will never know what is the underlying F, the underlying relationship. Nobody can tell you. So working with real data, this is one big shortcoming is you don't know the truth. You never know the truth. But that's why we work on a lot of simulations. So let's play the God role first. Let's put a F there. Then we simulate some data. We know this data follows this relationship, right? So we just draw a F here. Let's use this F as the truth. And plus some noise. Let's define the size of the noise, plus some noise. So we can make up some data set. So this is the God's part of job, generating a data set based on some F. Then we kind of hide these things we shouldn't know. In practice, we only see these. Then we apply our algorithms, try to figure out whatever the relationship is. Since we're playing the two roles at the same time, so we can compare our conclusion, our final relationship, how far away it is from the truth. Okay? That's the beauty of simulation. In real data set, you will never know that, but only by simulation you can do that. So we'll do a lot of, later you'll see we'll do a lot of this kind of make up a data set, and sometimes we really want to make a super difficult data set so that we can see some tools actually work in that special environment, some don't. So we need to do many experiments. And how to design such experiments is really important. Next week we'll spend time on some of these things. Now suppose somebody has done that, right? Somebody draw this line, determine some numbers for the size of the noise, and give you some data set. And the illustration here is the impact of the size of the noise. Therefore, think about, we are playing the God's role here. So we keep the same F throughout, but we change the size of the noise, the magnitude of the noise in these 4 different scenarios. So we are simulating 4 different scenarios, and we are applying our learning method. And let's see, in these different kind of scenarios, is that working or not? Right? That's the idea. But just by looking at the data, you can tell if that's going to work. Right? So when the noise is tiny, this is a trivial task. You don't need to spend too much time. This is an ideal situation where you have a little noise. But when noise goes larger and larger, the noise is too big, actually dominates the underlying true pattern relationship. Right? You know from the God side, you know the true pattern is this inverse S shape. But the one is too noisy, somehow you lose that piece of information. So when you do, if you're kind of electrical engineer, this is the signal versus noise. Right? The noise is too much, then you lose the signal. So let's see how the algorithm would work. So that's not really identifiable, but there are 2 lines here. The blue one is the truth. We said we're going to compare with the truth, right? Blue one is the truth. Red one is, I guess the red one is the from some estimation. Right? 3 or 4 weeks later, we talk about how do we estimate this thing. But this is an easy task. So you get some line. You can see when noise is small, as expected, we get a perfect fit. The answer we got is perfectly the same as the underlying truth. But when it's too noisy, there are going to be some gap. Right? So this is to show you the impact of the underlying noise. But the noise is not under our control. This is reality. So sometimes if you're lucky, you have a good problem here. But sometimes, most of the time, life is here. Yeah. So we should have a way to measure that. I will come back to that slightly later. And inside supervised learning, there are 2 further subgroups, and this is important. One group is called regression. The other group is called classification. The difference here is what kind of a Y we are talking about here. In supervised learning, we always have a Y, but a Y can either be numerical, some numbers, stock price, demand, and some numbers, right? Or Y can be categorical. We just say categorical can be like we send this coupon to this teenager goes, Dad, would that coupon be used? Right? That would be a yes or no kind of question. There are only 2 possible outcomes. That's why we call that categorical. There are only 2 categories. This data point will eventually fall into one of the categories. And yes or no can be arbitrarily defined. Sometimes we call that 1, 0. And the tradition is 1 means true or yes. It doesn't matter, no matter how you label that. If you use, this is stats tradition. In computer science tradition, they use +1 and -1. Yeah, and it doesn't matter, it's just a name, right? And category, this is the simplest case. You have two categories. This is the so-called binary classification. So you eventually you need to put the points into one of the two categories. Right? It can be a kind of more than two categories. I didn't put it here. But this is again yes or no. Let's not think about that. Let's think about the outcome of that game. It can be win, draw, lose. Right? That's three possible outcomes. So this is a multinomial classification. There are more than two categories. Multinomial classification is a bit difficult. The tools we're going to do mostly work with both, but some of the specific tool only works with binary. So binary classification can be simplified a little bit. So is that clear? There's a difference. One can be numerical, one can be categorical. Right? Now, question. Do you think there's a clear cut between the two? Can you imagine in some situation you might need to struggle a little bit whether we go regression or go classification? Good. 1 and a 0. Yeah. So when the number, when the y takes value 1 and 0, you can treat that as a binary classification. Alternatively, you can treat that as numerical. But most likely you wouldn't do that because classification is easier in this case. But sometimes you may have 0, 1, 2, 3. Right? Think about if we need to talk about a number of red cards. If we need to predict the number of red cards, if we check out the history of all the football games, at most there are 3. Let's make it 3. 3 red cards. So let's say the possibility will be 0, 1, 2, 3. There are other possibilities, but we just neglected the crazy situation. 0, 1, 2, 3. Do you think it's better to be categorical or better to be numerical? Why? Because I write it there? No, it's not an easy question, easy thing to answer. So intrinsically, it is numerical. It's a count about something, right? But the count is a small count, so it doesn't have many possibilities. So you can either put it here or there. That's really.
Sorry, so can I say that it is kind of like finite kind of thing that is categorical?
Yeah, if it's infinite, definitely cannot be categorical. It must be categorical. You have to define.
Just like just a finite kind of.
Finite is a necessary condition for categorical. It must be finite. You have to be able to specify all the categories. Otherwise, you cannot do that. But even if finite, if it's a million categories, that's not an easy thing to do. But so this is not an easy question. Yeah? I have another problem. So now let's think about this. Can be put up and can be put down, right? Either way, we don't lose too much. What is the fundamental difference if you put number of red cards as a numerical, or if we put it as a categorical? What's the fundamental difference here? There's a critical difference.
Prediction will be continuous for regression.
No, for regression you can later. I will show you. Actually, we can do discrete. Like we count the demand of product can be discrete. It doesn't have to be continuous. There's Poisson regression. There's other regressions give you integers. Yeah. but there's a difference. Yeah, in what sense? You're getting close, but in what sense? No, I just say I have 4 numbers. Here I don't really limit the numbers, but yeah. Here I don't really I just put it as a count, positive integers. But think about if anybody see this?
Like the variation of the errors.
How to measure the errors?
Yeah.
That's related. That's actually a good point. How do we measure the errors? If it's numerical, if the true number of red card is 2, you predicted 1, your error is 1. You calculate the difference. But if you think about that's categorical, these are just 4 categories. If the true one is 2 and you predict 1, you are basically wrong. You don't have a concept of how wrong I was. Because it's just 4 categories. You guessed number 2 and it turns out to be number 3. Right? That's exactly that's what I'm trying to say. If you put y as numerical, 0, 1, 2, 3 has the meaning of 0, 1, 2, 3. That has a magnitude there. Right? 2 is 2 times larger than 1. But if you put that as a categorical, these are just 4 labels. They don't mean anything. You can replace that 4 labels with red, yellow, green, blue, if you like. They don't have any relationship, right? So that's the intrinsic, the built-in assumption when you do categorical. The categories don't have any ordering. Categories, by definition, are not ordered. They are just parallel labels. And if you really want to, there's an ordered classification problem. That's a ranking problem. You need to rank. That's a bit different. That's not the same thing. But when you do numerical, they are numerical values. Then they are natural orders. Right? They're naturally, you can order any values as a numerical value. Right? So that's about basically that's the same question. The score or the number of red cards. So in that sense, you can convert a numerical to a categorical without taking a big risk. Right? 0, 1, 2, 3. If you believe that's numerical, just replace that with labels. You don't lose too much. You lose the orders, but you are still okay. But if they are not really ordered, if it's win-lose draw, and you force them to be 0, 1, 2, that makes a big mistake. Right? If you relabel them as 0, 1, 2 and put that as a numerical, that's a big mistake. So this sounds like trivial at this moment, but very often you see some data sets, you get your y being labeled naturally by 0, 1, 2, although they mean some 3 categories. They don't have any relationship, but people tend just label things that way. And if you don't just really understand what the meaning of that, you just treat them as numerical, then that's a big mistake here. Okay. So these most of the time this is trivial. Most of the time we study the project, we see the data, we define what are the y's we want to study, and we know we are doing regression or classification. In some very tricky cases, you might think twice about are these the right thing to do. All right, that's about supervised learning. And next is unsupervised learning. I just said unsupervised learning is difficult in the sense that nothing is defined. There's no objective, there's no right or wrong. Yeah, you do whatever you like. So it's very hard to do something. The definition of unsupervised learning is the table in your data is only a table of X. So everything is X. You don't know, you don't have a Y. You don't have a clear objective what you want to do. You just have a table, right? So what can you do with a table of numbers? And most of the time, people think about using unsupervised learning. They basically think about two things. Let me put it out here. I'm not getting into the details, but these are the two tools we are going to cover towards the very end. But the tools are basically used to reduce the dimensionality. So it doesn't achieve a nice prediction or those things, but it's really about dimensionality. So think about the table. We said we'll use this notation throughout. We have n rows and p columns. And we said this is the dimensionality of my x. And in this case, I don't have a y, but that's okay. So very often, this x is just too massive. You want to shrink that in some sense. I'll give you a more concrete example. But there are two set of tools. Clustering basically groups the data points together. So one data point is one row. So clustering try to group the data points into a smaller set of groups. That's basically reducing the number of data points. Instead of working with 1 million points, I'm working with 100 groups. Right? That's easier. I want to put them together. A quick way is to think about customers. You want to deal with all kinds of customers, but every customer is different. There's so many types. I want to group them in some sense. They say these are the double income, no child kind of a typical stereotype. They are groups, they behave the same thing. That's based on some belief, you put them together. These are the university professors, they behave the same thing, right? So, and in the future, you don't have to deal with all the individuals. You think about the stereotypes, right? And PCA works on, this is clustering. PCA works on this side. PCA says, you give me a sheet of data, but maybe some of the X are redundant. I want to identify which column is redundant. Right? This kind of a ridiculous example is you have one column for temperature in Celsius, the other column for temperature in Fahrenheit. It's clearly redundant information. And if you don't know, suppose you don't know the physical meaning of these two columns of data. Nobody tells you this is all temperature. You will never know they're redundant. But there's some algorithm to identify actually these two columns are perfectly correlated. Right? So you don't really need two columns there. So this is some algorithm to shrink your data to get rid of some redundancies. Principal component analysis. Principal components. Basically it says, I have P columns. Actually, I just need several components to represent everything here. Right? That's a principal component.
Okay, let's say we have a issue, we started with unsupervised learning. We
Uh-huh.
have our training set.
Mm-hmm.
So we just have we don't have a target, we just have a training set. So we created a cluster.
Mm-hmm.
So over the period of time, let's say we have built a substitutive model, it would cluster all the issues properly. So can that output can be used as a training set to be converted to a...
Exactly. That's the next line. Why people are doing this? Because the data is too massive. People don't want to work with 1 million data points. So we cluster them into 100. And we can analyze the behavior of these 100 different groups of customers in some sense. Right? So yeah, that's most of the time. Yeah. Do we have...
You're putting here that actually, so this clustering and PC is only applying on the X,
Yeah.
not on the Y.
There's no Y in this world. Yeah.
It can be Y, right? It's just that it's no Y, but it can turn out to be a Y.
Yeah, so you can later say, yeah, actually one of the column is the true Y I'm interested in. Now let's run the supervised learning now, after you reduce the yeah, exactly. So that's the typical kind of way.
So the supervised learning, do we apply similar tricks to simplify the data?
Yeah. You can use this, but when you talk about supervised learning, basically there's a Y column on the side. You can still say this X is too wide. I want to shrink that. No, I mean PCA you can do that. When you do clustering, you have to take Y into account. That's another story. When you combine things, you need to take Y into account. You cannot ignore that. That's no longer called clustering. Clustering by definition is a cluster only based on X. There's no right or wrong. I'll give you a better example. I think this is a bad example. Yeah. I've been trying to find an example for clustering for many years, and this year I found one. So I have to tell this thing. Think about color. The supervised learning version of color problem is you want to teach a kid to recognize the colors. 2-year-olds, you show pictures, you say this is blue, this is red, this is yellow. This is supervised. The kids, their eyes get the signal of the colors. That's the input, and the word you talk about is the Y's. The kids connect the signals with the word. This is, whenever I see this, this is blue. Whenever I see this, this is yellow. This is supervised learning. That's simple. But think about who defines what is blue, what is red, what is yellow. When humans start to develop language, who defines color is a continuum. It's actually high-dimensional, several dimensions. Right? How do you say these groups are blue? Not everybody agrees on the boundaries, probably, but who defines that? So and that's done by clustering, basically. Think about it, there are millions of colors. If you want to measure, probably millions of colors. How people cannot work with millions of colors is exactly the dimensionality. We cannot communicate. We cannot just give a million names to colors. That doesn't work. So just people don't want to work with such a high dimensionality. So we have to shrink that, say, group some of the similar things into groups. And we just work, anything within that group we just call blue, right? But there was a nice article on Quora talking about colors. So I got the insights from there. They were talking about rainbows. So every major culture, they see rainbow, they say, hey, there are 7 colors in the rainbow. Almost every major culture say that. You think, why 7? Rainbow is a continuum. Why everybody agrees there are 7? It's like you have a million colors in that color band, but everybody kind of agrees there are 7 groups. People shrink that, cluster that into 7 groups. And then somebody said, actually, in some tribes in Africa, they don't have a concept of blue. They have 6 colors. And they put blue and green into one cluster. They don't differentiate that. We might laugh at that, but there's nothing wrong, right? Why 7 is better than 6? That's exactly the issue here when you do clustering. There's nothing wrong. If I want to have 2 clusters, everything's black and white. There's nothing wrong, right? It's not good for communication, right? If you can come up with 20,000 colors, that's also fine. But yeah, that's exactly the point of clustering, right? And that example also shows clustering actually happens, this unsupervised learning happens before the supervised learning. You have to cluster them, give them a label, so that you can teach others, hey, everything here is green, right? So that you can supervise, you can teach others. So that's exactly the pre-processing part.
In general, is there a sequence that you do clustering before PCA, or you do concurrent?
Think about if it's a classification problem. Think about color. Color is not ordered. If you want to classify light signals into colors, you cannot work with a million categories. So you have to shrink them. And therefore, you have to make a decision how many groups you want. So that's classification has that problem. You need to decide how many categories of Y you want to have. Sometimes even just win-lose your said 3 is too many. Maybe I just predict win or not win. I combine lose and draw. I can use binary classification. So how many categories is really a human decision. That's related to color because they're not ordered. Really, you can combine them. If it's numerical, then doesn't make too much sense to shrink that. Anyway, that's continuous, that's numerical, that's infinite. So you don't need to do that. So it's mainly on the labeling of categories in classification. Yeah, it depends on your task. Like I was talking to my friends working in, they're doing this internet finance. They want to do credit rating to these borrowers. These guys borrow money using their phone app. How do you know their credit? But they have a lot of data of history. I said, isn't it quite standard? Credit card companies have been doing this for 20, 30 years. Based on history, they can do a credit rating kind of a model. I said, no, we actually struggled a lot on defining what do we mean by default. It's not black and white in practice. You borrow money, you have a deadline to return. Some people forgot to return that. You make a phone call to return the money the next day. Is that default or not? Some people say, I don't have money, give me a month. I'll return your money. I'll talk to my mother to get the money and give you the money after 3 months. Some people, at the time of borrowing money, they didn't plan to return. How do you define a default? It's not black and white. So when we do credit rating, we actually have multiple categories. So they were saying, these are the good guys, they're always returning the money. These are the guys, they might return if they have the money, but they really have trouble. They have not really stable income. Then there's another group, they will never return the money anyway, even they have money. So it's a big decision how many groups to put it there to do your credit rating. And they were struggling a lot on this thing. Yeah, it's not easy question, actually. Not easy question. And I have a conjecture here why people tend to have 7 major colors. My conjecture, let me do it here. I think this can be a good project for this class. Think about if we can measure color on a continuous scale. So we have 1 million colors. What if it's just one-dimensional? What is clustering? Later we'll talk about exactly how clusters works. But really it's look at the frequencies. It's really not looking at the physical attributes of light. It's not about that. It's about the frequencies. So say you see a lot of colors here, then just in everyday life, right? In the nature, you see a lot of colors here, you see some colors here. And people tend to say, I'm more familiar with this group. And that's one group. That turns out to be red. And this is green. Think about in the nature, red is much more common than pink. Right? I'm not sure how to define that, but think about green is very common. Blue is very common. You have a green forest, and we have blue sky. These are the colors show up with very high frequency, right? So that determines how do we group them. Later you will see the clustering algorithm really actually is here. It's really based on the frequency. Let me go through this thing. This is we're coming back to this example when we do clustering, but this is basically 3 groups of data. But we are telling you the answers. This is a bit cheating. Imagine these are just black dots. These are just a bunch of black dots. Everybody see this picture can immediately say there are 3 groups of dots. There's not much controversy here, right? And because they're close to each other, there's high frequency around this, high frequency. Color can be the same thing. And there's a just nice separation by frequency, right? So without knowing the answer, reasonable people can put them into 3 groups. this is the same three, not the same, another three groups of points, but without the label, think about they're just black points. Then that becomes controversial. Are these one group or two groups or three groups? And different culture may define different groups of colors. Yeah. So that's clustering, right? That's based on the frequency, based on the distance, similar. Right? So I was mentioning this can be a project that you can go to Google Image, download 1 million pictures about nature, and calculate the frequency of colors show up in the nature. You should see some very high spikes around some colors. That should be corresponding to the major colors we're talking about, I believe. It's just a conjecture. Are we okay? Okay.
What is X1 and X2?
Just some X. Don't worry about that. Right?
So why is no X and Y?
No, this is clustering. There's no Y. Remember, when we talk about clustering, you only have X. So this is simple data. You only have 2 columns.
Yes.
Think about, yeah.
Hard to understand that why the horizontal is X1 and vertical is X2 rather than Y.
No, there's no Y. There's no Y. It's just a bunch of students. You ask everybody what's your income and what's your age. Just 2 numbers, and you will just plot this. Right? Just 2 numbers. You can always plot that. Yeah.
About this problem statement of the color,
Mm-hmm.
coloring. So I understand that humans can recognize this 3 colors. Something to do with evolution.
There's some biological reason.
They don't recognize all these 3 colors.
Yeah.
But processing the image, for example, we have this kind of pattern, red, green. But then how to explain why mammal, some other mammal like birds, they see more colors or they see less colors?
We need to first know their clustering outcome, how they cluster. Yeah, right. You have their signals. Yeah, probably you can get their signals, but you don't know how they group colors. So that's another story. Right. This is really, when we have language, we need to communicate. We have to give them labels. Right. Yeah.
So what is the better way? I mean, when we have unsupervised set of data, should we specify the lower number of clusters to start with, or?
No, there's no answer. There's no answer. So 7 colors or 6 colors, which is better? It's always a trade-off, right? This ease of communication, the accuracy, right? The more color you have, this more accurate you describe things. But yeah, there's a cognitive kind of burden out there. Clustering, unsupervised learning, there's no way to compare. You do your side, do mine. Yeah, we don't need to agree with each other. Right? Mm-hmm. Mm-hmm.
Because you were saying that actually that you do the clustering, the whole entire X, the data inside, right?
Mm-hmm.
So by having X1, X2, which you already separate them out.
Yeah.
So if I relate back to the withdraw as in clustering is actually on the vertical, which is 1 to 3 all the way to n.
Mm-hmm.
1 to p is actually your.
Yeah, here P is 2. Yeah, P is 2. Oh, there's only 2x, right? Here, I forgot about it. Here, P is equal to 2. So your x is basically x1 and x2. You only have two measurements of every data point. Right? Did I?
So how do you get x1, x2, and you do the PCA, then you...
No, that's just give...
x2, then you do clustering? Because you...
It's a good point. Actually, that we will do that later. We'll do that later. Yeah, that's a good point. The question is, if you have a massive data with many columns, do you do clustering immediately based on all the columns, or do you do PCA and shrink that redundant columns and then do the clustering? We will do that, and there was an example showing PCA actually helps you do the clustering. If you just cluster directly, you don't see the nice separation. But after PCA, you can separate them. That's a good point, yeah. But I think that's a real difficult thing. In learning each of the individual tools is simple, but in what sequence do you run them? That's not easy. That's not easy. Yeah.
Let me see if I get this right. So, for example, your X1 is the age of a person,
Mm-hmm.
and X2 is the number of hours they sleep,
Mm-hmm.
and I want to cluster them into, well, the toddler sleeps this amount of hours.
Yeah.
Maybe I just want to do it 1 to 2 hours, 3 to 4 hours, or I can cluster them as 0 to 5 hours,
Yeah.
and then 5 to 10, and so forth.
Yeah.
And I can cluster. Sorry, that would be PCA.
This is cluster. This is cluster. Yeah.
Okay. And then the age group, I can be the toddlers, the teenagers, and then people, or
That's the outcome. So think about this is the age. This is the number of hours they sleep every day. So if you plot the data, if you happen to see something like that, you will say, these are the young guys sleep very few hours. These are the active kids. These are the young but sleep very long. These are the lazy kids. So that the label actually comes after that. So you first get the groups, then you look at these guys. What are they having in common? Then you give them some name. Like this double income, no child. It's not really defined by somebody. It's really people observe, hey, these people behave the same way. Why they all behave the same way? Because they have money and they don't have kids and they have all these things. It's really the backward. Yes. They see the cluster, then they find how do we name these guys. Naming is arbitrary actually, but there's some message out there. Yeah. Yeah.
Sorry, just again on this example. So in this case, you have two columns of X and Y.
Yeah. X and 1, 2.
And in each X, 1, and 2, you have many different values, right? From 0 to 12, 0 to 12, 1.
No, just one number.
Right. So different values are from 0 to 12. Of each
0 to 12. What do you mean? Is age?
Because you have a column X, 1,
Mm-hmm.
and the values range from 0 to 12.
No. Yeah, that's a range.
Right.
Let's imagine what the data look like. So you only have x1, x2. Data number 1, say this guy. x1 is 2, x12, x2 is 12. This guy is number 2. This is 4.5, 6.2.
Right. So you have a range of numbers from 0 to 12 on each column, right?
Yeah.
Now, when you do clustering,
Uh-huh.
you're grouping into 3 different categories,
Uh-huh.
and you're reducing the columns as well.
No, you're reducing the number of rows. So I didn't explain. Yeah. No. After this, you don't really deal with all these 100 data points. After this, you say group point 1 and 2 are labeled as blue. They are in the blue group.
So you still have more rows.
No, I'm combining all the blues together.
Oh.
I'm aggregating how much money the blue guy spends on everyday transportation. I'm averaging them. Say the blue guys becomes one row. The blue team, what's their number? What's their measures? I'm aggregating them. Yeah. At the end, I only have 3 teams: the blue team and red team, the orange team and green team.
So would you say clustering reduces your row?
Yes.
The rest
Just
of PCA reduces your column.
yeah, exactly. And then you only work with the 3 data points in some sense. Yeah, think about if you have many.
So you have 3 rows.
Yeah. Or you can, instead of treating this as data point 1 and data point 2, you add another. You can add another X3. That's their labels, blue. You can use that as an attribute later. In some other, yeah. They belong to that particular stereotype. I don't have a good example like doing this throughout, combining unsupervised and supervised. I didn't find a very convincing example out there actually. Something missing actually.
This graph X1, X2 is after PCA. So after PCA, we will create new variables with new variables. How do we interpret?
PCA you can interpret. Leave that question to week 12. That PCA is interpretable. Don't worry. Yeah. Think about the stock market index. How do we interpret that index? That's a weighted average of all the other things. Right? PCA is a new number, weighted average of anything. Right? I need to run a little bit quickly. So a bit on, are we okay? Okay. So the details will come back later. This just to show you what will be there. A bit kind of on this territorial fight between the statisticians and the computer scientists, and they all have their own jargons that they don't agree on each other. But eventually, at the end, they really do the same thing. So there's some different perspective, different mindsets. So I'm trying to clarify a little bit. So machine learning comes from computer science. Statistical learning comes from statistics. And the machine learning focus more on the outcome, accuracy. I'm predicting, I just want accuracy. I don't care how to interpret this model. If I can predict the customer is pregnant, good. Right? Accuracy, and the large scale is another thing. So this often comes with large amount of data, the big data thing, because they're good at that, right? Statisticians work with small data. 100 data points, that's statisticians. So on the stat side, we tend to focus more on the interpretation. On top of being able to predict, we really want to say why. Why and what is driver, how much is the weight, the contribution of each drivers, all these things. Right? On top of precision, we want to say something. This is related to the field econometrics, like applied statistics. That's social. The whole social science is basically trying to get some data and trying to make up stories why things happening that way. Right? Why is more important. And the other thing I didn't put it here is about causality. In stats, causality is a big thing. On top of understanding X can be used to predict Y, we want to know which is driving which. Like the stock market is related to the future market, but which one is driving which one? That's important because if the future market is driving the stock market, then you see some fluctuation here, you can predict the stock market is going to fluctuate. But if it's backward, it's actually the stock market is driving the future market, and you see some fluctuation in the future market, it doesn't go back to the stock market. So there's some causality things. Computer scientists don't really worry about that, and they don't believe in these things. Yeah. So and again, over this whole course, we are going to focus mostly on the tools, but I want to highlight the importance of identifying the right problem, get enough good data is in front of that. Being able to use the right tool really comes in the third place. But we teach the fundamentals, the simplest things, how to use the tools, how to understand each of the tools. And there's a higher level workflow. We'll come back to that. But have you seen the data robot thing? This data robot guy came and talked about this thing, right? Yeah, but bad news is everything I'm teaching here can be automated by data robots. You just need to import the data, click start. It does everything we teach here automatically. Not in a smart way, in a brute force way. Just try all the things. If it doesn't work, it doesn't work. Right? Just try. Right? I'll try to make it not working. I will try very hard to make sure. Import the data and click start, it will not work. But I still think it's important to understand this thing, understand each of the tools, what the places it is good at solving the problem. Some of the places it doesn't work at all. You should have some understanding. Yeah, but yeah. So a quick overview of what's going to come. Let me just list everything. So in the following 11 weeks, we're going to cover all these things. So the first big family is regression. So this is basically, this regression is not that regression. Yeah, it's not exactly that. This is about a linear regression. But this is about the big family of linear models. Linear regression is the classic things coming from statistics. Then we have a modern version of that called the lasso. Lasso. This is the best thing in this family. Towards the end, we will do a lot of comparison what classic statistics can do and what a modern tool can do. And lasso dominates linear regression in every single sense. So yeah, after learning that, you shouldn't use linear regression anymore. And the other this is about a linear family. Earlier I talked about Poisson regression, logistic regression. So these are for Y's that are discrete. Poisson is for counts, and logistics for categorical. Yeah, so they can solve all these questions. Then we have the tree family. So these are the nonlinear families, trees. The important ones are these two guys. And these are the tools people use to win the Kaggle competition. Almost all the winners use boosting. Random forest as the first step. Yeah. These are good tools with super high accuracy, but there's not much story you can say. It just gives you a good prediction. You know nothing going on inside. It's not a, but Lasso on the other side, Lasso provides good prediction accuracy, but at the same time gives you very simple interpretation about what's going on. There are two important things crossed out: support vector machines and the neural reason being. This is a sensitive part. I should take it off. So we had a big fight on what should be covered under the umbrella of statistics, what should be covered under there's another course on machine learning. And eventually we reached an agreement. Let's draw the line. Whatever tool invented by statistician should belong to me. Whatever tool invented by computer scientist belongs to that guy. So he took the other two. So I'm having more. So these are all coming from the stats literature. But anyway, I don't think they're super important at this moment. Having this big framework of understanding these things, learning a new tool is really trivial. Having new things, and in the future, in your code, only the last bit is about applying this lasso or random forest to do the prediction. And if you learn the new one, neural network, you can just replace that line of code. That's yeah. And on the unsupervised learning side, I have mentioned we will do several clustering algorithms than the PCAs. So these are the tools. The fundamental ones, everybody should have some understanding about that. And then on top of that, the important thing I mentioned about the workflow that's related to cross-validation and bootstrap. These are more important. And getting the right workflow, like whether we should do PCA first or clustering first, these are the more critical things. How do we cut the data into multiple pieces and use the data in different places? Only 20 minutes? I haven't reached the important part. Let me just quickly go through some minor things. Do we have questions over here? Or request? Do you think there's something I should include here? Deep learning is too deep. I cannot dive in. There's not much to talk about, actually. So next part, let's think about a simple supervised learning context. So from now to week 10, we will do supervised learning. Right? Everything is the simplest. So the question here is, how do we measure the accuracy if we come up with some estimated f? How do we measure the accuracy? Again, we would illustrate this by a simulated data set. We have the true f in this blue surface. So think about income is our y. So we want to predict the income. We have 2x, years of education, and the seniority. This is x1, x2. Right. So we can plot the true f. This is the two-dimensional instead of one-dimensional. But yeah. But there's nothing more complicated than the previous line. Right? That's a true f. And we need to have some noise. So we generate some data points that is coming from this true surface. Then we add some noise, then they move up and down. Some of the unlucky guys, they have the negative noise. They have lower income. Some of the lucky guys, they have positive noise. Right? And these red dots becomes our data set. So again, supervised learning, we need to find out that some function f that is as close to this as possible. Right? So, and there are two standard ways to think about that. Earlier, I have a list of tools. Some of the tools belongs to the parametric family. Some of the tools belongs to the non-parametric family. This is not super important in the execution, but yeah, let me just quickly go through that. The parametric family basically says, I know there's an f, but how do I come up with a guess about that f? Let's make some assumptions. Let's start with some shape. And the simplest shape, if you have no idea, is a linear shape. Let's assume everything is just a plane. Right? In one-dimensional, it's just line. Two-dimensional becomes a plane. Right? Just assume that. And that's a big assumption that may not work. And you have seen the true f is not a plane. Right? So at the moment of making this assumption, you're losing a lot of accuracy already. The best plane you can find cannot give you perfect prediction. Right? But in practice, because you never know the true thing, so you come up with that as a starting point. And once you have that functional form, this is an easier problem. We just need to find out the betas. If we have the betas, we are done. The betas determines where to put this plane. Right? These are the coefficients. So instead of thinking about how do we describe an ugly function, we just need to find these betas. Then we are done. Yeah? That's a good part about parametric. There's very compact representation of that function. Several numbers is enough. So that's the outcome. So if you try to, this is a linear regression. Later we'll come back to this. But if you find the best beta, because we only have two x here, so we have three betas, the one intercept plus the betas for each variable. And you can see that doesn't fit perfectly, but good enough. Right? Captures the major pieces of information. And this is why social scientists like that. Now you can make up stories. Like for every extra year of education, the income goes up by beta 1. Right? So you can say things like that. This is a parametric. Why people want to use that? Because you can say something about the underlying structure. Or you can say every year of education, extra year of education can replace how many years of seniority in that sense. It makes you equivalent. Non-parametric, there's people from the other groups don't like making assumptions at the very beginning. They said, I don't want to assume anything. I just want to describe the curvature I find from the data. And the good thing is you don't lose the accuracy by your assumptions, right? The bad thing is, how do you describe this surface? And you need to, you cannot just draw that, right? How do you describe the surface? How many numbers you need to describe that? It's not easy. But there's some solutions to do that. But yeah, let's not go there. In general, that's not really the concern most of the time. Most of the time, the concern, if you just want accuracy, you just run whatever method you have learned. Do a horse race, choose the best one. That's data robot. Just apply all the possible ones and do a horse race. Whatever, parametric, non-parametric. But if you really have to make some stories, and you have to stay on the parametric side because that's the only place you can say something. Let me skip all these things. So the trade-off is really on the, if you want to say something about the outcome, there's an interpretation capability, interpretability, that's a parametric. And also parametric give you a more parsimonious way of representing things. Several betas would be enough. But the key thing is really here, why people want to use a simple model to represent the F. Although they know the simple model may not fit perfectly, people still prefer a simple model. The key thing is not about the interpretability. The key thing is really about overfitting. And that's the fundamental concept for today. I think I'm coming back to overfitting in one slide. So back to interpretability, we have these tools. I took from the textbook. So some of the tools we're not going to cover. But this kind of a diagram about trade-off. The more flexible your model is, the more accurate the prediction would be, but you will have less interpretability. This becomes more and more a black box kind of thing. Boosting is the most accurate kind of a tool out there, but really there's nothing you can learn from boosting. It just gives you a number. Lasso, I don't agree. Actually, Lasso should be roughly here. According to most of my personal experience, Lasso doesn't lose too much from boosting, but at the same time, Lasso has all these beta 0, beta 1, beta 2 kind of stories you can talk about. And yeah, that's not important. All right, finally, we have several minutes on this, the most important message. Overfitting and fitting, right? So we're talking about, we have a prediction, there's a true F, and there's our estimated F. And here, the estimated F is F hat. So instead, everything you want to the estimate will have a hat there. If you want to estimate A hat is your estimate. Right? So F hat is the estimate of F. So we have an F hat. We want to know how good it is. So we want to measure the accuracy. In the kind of domain of regression, let's just talk about regression first. There's a numerical Y. So measuring F hat is easy. So the standard measure, there are multiple other measures. The most standard, the most commonly used is a mean squared error. The formula is over there, not very complicated in that sense. So let's look at this backward. Where do we see error in this formula? yi minus f hat xi, right? Yi is the true y of your data point. F hat xi is the predicted value of your function. Right? The difference is the error. Ideally, it should be 0, right? But there's some difference. Then there's a squared term. We don't want to just aggregate the errors. We want to take a square, because sometimes the error is positive, sometimes the error is negative. You just sum the error, they cancel out. That's ridiculous, right? So there are two ways. You take a square, or you take an absolute value. That makes the two commonly used. Mean absolute error. If you replace the square with absolute value. Then we have the mean part. Mean comes here, right? How do we calculate the mean? We sum them all together, divide by n, right? That's the mean. That's the mean part. So mean squared error. That's the standard for regression type of problem. Most of the time we use that until you have a better reason not to. Right? Better reason including sometimes y is positive, like a stock price. People don't care about the absolute fluctuation of stock price. People talk about the relative fluctuations in terms of percentage. So you need to do a log transformation. So people will do a mean squared log error. You can do a log here. That's mean squared log error. Right? That's MSLE. In many of the sometimes people don't like mean squared error because this is a square thing. When you talk about your error, you want to say this is dollar, this is dollar. My unit for my mean squared error is dollar square. How do we understand that? So sometimes people say let's do a root. Let's do a root out there. That's the root mean squared error. That's RMSE. Just to take a square root so that the unit becomes dollar. It's easier to understand. But there are all these different measures. They're not very different. Most of the time when you participate in a Kaggle competition, they will tell you, these are the data sets, these are the criteria we are evaluating all the participants' prediction. We are doing this root mean squared log error. So we rank people by this, so you have to optimize by that. But in other situations, yeah, mostly people don't bother change those things. This is how we calculate the error. That's not a key question. That's just a formula. Right? Excel can do that. If you give me xi, yi, a table, Excel can do that. The key question in this part is really where do we measure the error? Where do we measure the error? We have a data set, y. We have a bunch of x. We have trying to get an f to measure f hat, to measure their relationships. After having this f hat, how do we measure the error? Well, we only have this data. So we go back to this data. We put xi, yi in our data set into this MSE, and we can calculate. This is a so-called training error. So the error we measured in the training data set. Training is, we use this data to train the f hat. Right? That's the training part. And this is a training error. So training error should not be used, absolutely not used. Training error is meaningless. This is one fundamental difference between modern and the classical statistics. In classical statistics, people are still using training errors, R square. Later you will see R square. R square is the transformation of this thing. This means nothing in the sense that, think about what we have been doing. Think about the training part. It's like you are learning some mathematics. I give you some exercises, and I give you some home answers. Exercises, the questions are the x, answers are the y's. By doing all these set of questions, you've managed to find what's the relationship between x and y's. Now I want to test how well you understand this topic. I should measure your accuracy. I should give you some questions, ask you to answer that, and I can measure your accuracy. But here, what we are doing, we are giving you the same set of questions when you learn your stuff. Tell me, what are the answers? That's absolutely cheating, right? Even the stupid people memorize everything, can get a full mark, right? You don't need to understand everything. You might understand everything, but nobody knows, do you really understand this thing, or do you really just memorize all the questions? Because my exam questions and the homework questions are the same, right? That shouldn't work. And that's the important thing. I'll have some illustrations. So then how do we measure the errors? we should have an exam. And the exam question should be different, right? That's reasonable. We should have another data set. We should have another data set. This is so-called out of sample. This is an in sample. In sample is you have a data sample, you train yourself, and you measure yourself within the same sample. That's cheating. The important thing is the right way to measure is out of sample. Give me another data set. Right? Hopefully from the same thing. Right? That's important. I cannot I give you math exercise and test you English. Right? So it must be the data sample from the same population, same model. This is the so-called test data set. You should have a mutually exclusive training and the test data set. They cannot have anything overlap, otherwise it's cheating. Right? So in practice, how do we do that? We don't have two data sets. We have the data, we use all the data to do the training. But in practice, we'll cut that into two chunks. We use the first part to do the training. We'll keep something for test, yeah? To test ourselves. And there's another data set. We'll come back to this a bit subtle. Let's not mess up here. But here, the important thing is when you measure your accuracy, you shouldn't use anything. You train your model, right? So let me show you the illustration. Again, simulation. Black one is the true F. The God draws, right? Then we get some bunch of data points based on the true F. There's some noise. The circles are the data points. So now suppose we don't see the black lines. Now we are back to the data scientist view. We see the bunch of dots. We need to find the underlying relationship, right? So there are three data scientists. The orange guy assume a linear relationship. He doesn't know. He look at the data, I believe this is linear. Let's find the best line represents this data. He end up having a orange line. And the blue guy, where's the blue guy? Blue guy choose some sort of thing. It's pretty much the same as the true one, so you don't see that. And there's a green guy. Green guy is the cheating guy who doesn't know anything. He just memorized all the data points. So his F hat actually connects pretty much all the data points. He goes up and down. He doesn't know what's going on. Right? Can you see that? This is about how do you cheat. You memorize all the data points. If you want to be more crazy, you can just draw a line connecting all the data, connecting all the points. And then later, when you measure your own performance on the same number of points, because you draw the line to connect these points, every point will be on your line. You will have a perfect prediction, right? But that's memorization. So that's the three guys. Then we need to measure their performance, their mean squared error. So we measure their performance on two things. The first thing is the training. Then we said this is the training guy. MSE in the training data. You can see the linear guy doesn't work really well, pretty high error. The blue one, all right. And the cheating guy get a very high score. His error is really low, right? And we know that's not the right thing. And as I mentioned, you can cheat more if you want. You can just connect things. You can get a perfect score. So that's not something we should look like. Only in this session or next session, when we do illustration, we plot this training error or in-sample error. That's something you shouldn't even plot. You shouldn't even look at that. That doesn't mean anything. Yeah? The real thing is the test error. So since we are doing simulation, we have another luxury. So we can simulate another data set using the same black F. Right? So we can have a test sample, another bunch of data, and we can measure the error of these three guys on the new set of data. And it turns out to be like this. It's not very surprising because you know which one is the best, because you know the truth here. right? The orange guy is here, high error, and the cheating guy now having high error, right? Why the cheating guy doesn't work? Cheating guy memorize everything from the training data, but when you have a different data, it doesn't replicate, right? A new data set doesn't carry the noise, right? The cheating guy basically memorizes the noises, not memorize the true pattern, right? It memorizes the noises. And the noise are just randomly show up. It doesn't carry to the following data set, right? So it won't work. So the cheating guy will have a high test error. And the real optimal one is the blue one, the one in the middle. Yeah, since here you can see it's closest to the true F. So this is the most important part we need to talk about today. The orange guy is the so-called underfitting. Underfitting in the sense that I come in and assume a linear relationship. That linear straight line doesn't work well to represent my data. There's clearly some shortcoming. I cannot model the curvature. So this is, I cannot fit, no matter what I do, I cannot fit the shape, right? Impossible, underfitting. That's by your assumption. You assume the straight line, that's the best you can do. There's not much mistake. This side is overfitting. Overfitting is you are giving yourself too much possibilities. You just allow any shape in your F hat. And having too much flexibility, by training that, you will naturally fit the noise. So the idea, because the data comes from F and noise, the whole idea is we want to capture F, not capture the noise. But when you have too much flexibility, you will capture the noise, right? These are the information not going to be carried over in other samples. So that's the overfitting part. And that's the optimal fitting is this guy, right? So the whole course on supervised learning is really on how do we find the right fitting, not underfitting, not overfitting. So by avoiding underfitting, we need the model to be flexible enough. By avoiding overfitting, we need some other ways of doing that. Here it's not so clear how can we not go that crazy. Right? It's not clear here. We okay? I'm running a bit out of. Are you okay? Doing several more minutes. So there's several other examples I'm not going through. The same idea. This is an kind of a universal pattern. Whenever you have a new data set to measure the error, it's always a U-shaped. There's a theoretical reason for that. It's always a U-shaped. There's always an optimal point here, and there's always an underfitting side and an overfitting side. Yeah? This is a universal. It's not so nice, but it's still, you can see this optimal somewhere in the middle. We just replicate these experiments with many weird shapes. It's always the same thing. One thing I forgot to mention here. This is the line. Can you guess what's this? There's a line here. That's the noise. Right? That's a noise driven by epsilon. This is a so-called irreducible error. That is the absolute maximum you can achieve. Let's say, even you know exactly what F is, because all the data comes with the error on top of F. Even you know exactly what F, you are subject to this error. Right? So your prediction cannot be better than that. That's the irreducible error. And by definition, your estimate F hat cannot beat this line. It should be always above that. And the training error is cheating, so it doesn't matter. So that's a nice thing. But in practice, it doesn't exist. You will never know. This is simulation. You play the gods rho. So you generate epsilon. So you know how big is epsilon. In practice, nobody can tell you. Yeah? You don't know where's the limit. That's the luxury of simulation. You can see by doing such a simple model, we are pretty much reached the almost close to the truth. Yeah? Okay, now let's see. We have seen overfitting and underfitting. Let's see why it always goes like a U shape. And there's a beautiful set of theory. Let me show you the theory first. It says the mean squared error out of sample. By definition, that's a mean squared error. Instead of using average, we use the expectation. That's the same thing. The mean squared error out of sample can be decomposed into 3 components, the summation of 3 components. We just mentioned the noise, the contribution of noise. Your out of sample error will always have the contribution of the noise. This is the irreducible error. Right? There's nothing you can do. You can never learn that noise by definition, and it stay there forever. So your error will be at least as much as this guy. Right? But the other 2 is about the error you have on your estimate of f. And this is the summation of 2 terms, and they have beautiful names. This one guy is called bias, one guy is called variance. And next week we will do some numerical illustration to show you the bias and variance. I'll come back to the definition that's deeper than that. But let me show you the picture first. If we have the U-shaped, so in all the 3 examples we have shown, we have the U-shaped test error. And we just say there's a theory saying the test error can be decomposed into the summation of the irreducible error, and this is bias, and this is variance. The summation of this is the irreducible error. Irreducible error sets the platform. You cannot go beyond that. Right? But the U shape is really driven by bias and variance. So in almost all the pictures, bias goes down when your model is becoming more flexible. The flexible part, we have been very loose. We didn't define what do we mean by flexible. It really depends on the tool you use. Next week we will define flexible. But think about inflexible is a straight line. Flexible is you allow your function to be up and down, right? Connect many points. So when your tool gets more and more flexible, you are able to reduce the bias, and at the same time you're increasing the variance. Right? So we didn't touch about what do we mean by bias and variance. But let me first show you the pattern. And these 2 guys determine the U shape, the universal U shape. Let me go back to the bias variance. Now we can stop. So what exactly do we mean by bias and variance? In statistics, right? I'm too tired. In statistics, the biggest question is, I have a population. I want to study the life expectancy of Singaporeans. The population is several million. I want to know something about this population. I cannot measure everybody, so I get the sample. I get the data set 1 and measure their y. And I get an estimate y hat 1 based on the data set. In statistics, the major question is really, because I'm joining data randomly from the sample, from the population. I'm joining 100 person here. These 100 guys are random. I'm randomly joining them. Therefore, the number I get, the estimate I get is random. It's going to be changing in the sense that if I repeat the same thing again, I will have another number. Pretty much, they won't be the same because I'm having another random 100 person. Right? There are fluctuations. And these fluctuations, so if I repeat this many, many times, I'm trying to guess what the estimate is. But if I repeat many times, I'm seeing these guys are fluctuating. But can I say something about the population? I can still say, but they just there's some intrinsic randomness because this is a small sample, right? So this is the so-called variance, and that's the same variance like there. Now put this in our context. We are basically doing the same thing. Instead of talking about some life expectancy, we're talking about some magic function there. Right? We get a data set from that population. We estimate that using whatever method. We have that. And if we repeat this, we might get something different. We might get something different, right? And our answer to this question is changing because of this data set. And that's not what we want. Ideally, if our method is perfect, we should get exactly F here, if we have a perfect method. Every time we get exactly the same F, then we should have no variance. They are the same. But our method is not perfect, so there's some variance coming out there. So that's the variance term. And this term plays a big role in the test error. Right? Because if every time you get very different things, you can imagine that's not going to be a very good algorithm. Right? Every time you're getting very different answers. So variance is a big term. And how about bias? Bias says, although these guys are changing every time if I repeat this many times, but on average, how good are these guys? On average. So bias tells us, let's do this F hat infinitely many times. Let's calculate their average. Are they close to the truth? Right? So one measures the central tendency. Are we close? The other measures how uncertain it is. And these two things contribute to the error. Right? Can we map this to this? So that's a formula, but that's the interpretation. Right? The whole thing is driven by the data set is random. Once the data set is random, everything you derive from that data set becomes random. When you get a different data set, everything becomes different. And in statistics, we really want these guys to be consistent. Consistent is one thing, right? Because every time you get the same thing, that's one thing. But every time you get the same wrong answer, that's also bad. So can you see this? One situation is every time I get the same thing, but they're all equally wrong. That's high bias, low variance. So that's a straight line story. That's earlier we have some data like this. Straight line is much like this. If you get a new group of data points, your line won't change a lot because it's really inflexible. Your line won't change a lot. But every time you're equally wrong. Right? This is high bias, but low variance. Right? So by using an inflexible method, your gain is, it doesn't change a lot because it's inflexible. No matter how your data change, it's pretty much the same thing. But the inflexible method gives you a higher bias. On average, you are still wrong. Now think about the other one. The other extreme, we are connecting all these dots. Right? That's our answer. Think about, get one data set, I'm connecting these. Get another data set, I'm again connecting these things. And this must be very different. So I'm having very high variance. Every time I have a set of exercises, I just memorize that. And student 1 and student 2 memorize completely different things. And their understanding about this subject will be very different. Right? There's a very high variance every time. But if you average these guys all together, what will happen? Think about every time you just connected, right? If you average these guys, you don't lose much if you repeat that infinite many times, right? So this is the low bias, high variance story, right? So that's exactly the underfitting and overfitting. Underfitting and overfitting is purely driven by bias and variance. Underfitting means you have high bias. The model is not flexible. Overfitting means it's flexible it's too flexible. So there's too much fluctuations. We don't want too much fluctuations. Are we okay? Next week we have, so here we just talk the talk. Next week we'll do one algorithm. I'll show you how to go from extremely inflexible to extremely flexible. And we'll see the underfitting and the overfitting. Okay. This slide, I don't need to talk about that. Just earlier we talked about mean squared error. That's for regression. For classification, we need a different way to measure the error because we are just comparing the labels. If the labels are the same, we are correct. Labels are not the same, we are wrong. So we need to count. All right, we're done. The final picture, this is what I want to highlight. If you can only memorize one thing after taking this whole course, memorize this picture. This is a training error. Doesn't mean anything in sample. This is a training error. The real one we should look at is this test error, but measured on the test sample, and it should be a U-shaped. And you have an underfitting, and you have an overfitting on the other side. And the whole field, all the algorithm, the difficulty part is really find the optimal fit in the middle. How do we find that? Good. Done. Oh, sorry about that.